Hello everyone, I'm Kento Hasegawa from KDDL Research, Japan. I will start my presentation entitled Toward Running Robust Detectors from Imbalanced Datasets, Liberating Weighted Adversarial Training. In this presentation, we focus on security applications of machine learning. A real-world security dataset is imbalanced. So the goal of this presentation is to construct robust detectors that learn from imbalanced datasets. Here is the outline of this presentation. First, I will introduce the background of this research. And second, I will introduce the related works on imbalanced learning and adversarial training. And then, I will elaborate the adversarial training method which is used in our proposed method, weighted adversarial training. Next, I will propose our proposed method, weighted adversarial training, which enables us to construct robust detectors for security use by considering imbalanced training datasets. After that, I will show the experimental results and analyze the results by visualizing them. And finally, I will conclude this presentation. So first, I will show the introduction of this research. In recent years, machine learning has become an attractive technique for security. And how to effectively use machine learning for security should be considered. From a security point of view, there are several problems in the use of machine learning. The major problem is that it is difficult to collect a good quality dataset. Typically, the real-world dataset is imbalanced. Since malicious behavior rarely occurs, there are only a few such samples compared to benign samples. We need to handle such datasets appropriately in machine learning. This figure simply illustrates the problem. In this figure, the blue samples are benign and the red samples are malicious. For security purpose, we want to catch all malicious samples. This malicious sample is misclassified as a benign class. This case is unacceptable because we want to catch all malicious samples. On the other hand, this benign sample is misclassified as a malicious class. This case is called false positive, and it is acceptable if there are just a few false positives. In machine learning, balancing this misclassification is important. So we address this problem in this presentation. So our motivation is to address imbalanced datasets of machine learning for security use. The contributions of this presentation are summarized as follows. First, we design weighted adversarial training to expand classification areas of minority classes. Second, we take two approaches, untargeted and targeted. And then we apply weighted adversarial training to an IDS using a traffic flow dataset. And finally, we visualize the classification results for further analysis. And next, I will show the related works on this presentation. First, I will introduce the balancing method. To balance the dataset, there are two approaches to handle imbalanced datasets. The first approach is data level. In this approach, we generate or reduce training samples to balance the number of samples for each class. Smoto is a popular method for this. However, it is difficult to generate or reduce training samples while keeping the distribution of the original datasets. The second approach is algorithm level. In this approach, we balance the training dataset by putting some weight to the loss function, where another method has been proposed so far. Next, I will introduce the adversarial example. Adversarial example is a sample that fools a machine learning model by adding perturbation. Adversarial example image look natural for humans, but unsophisticated classifiers may misclassify them. The figure shows an example of that adversarial example attack. By adding noise to an image of a panda, a machine learning model may misclassify the crafted image as another animal. In order to tackle the problem of the adversarial example attacks, some defense methods have been proposed in recent years. One of the approaches is adversarial training. Adversarial training makes a classifier robust against adversarial examples by training adversarial examples themselves generated during a training iteration. And next, I will explain the adversarial training in detail, which is used in our proposed method. In this section, I will introduce one of the popular methods of adversarial training, projected gradient descent, or PGD method. There are roughly 2 steps: generating adversarial examples and training it. First, we calculate the gradient of the loss function with respect to a given sample. Then, we get a direction to increase the loss of the model. If the loss of the model is increased, the model may misclassify the sample. And then we move a sample by alpha towards the calculated direction at one step. We repeat this process for several times. The maximum moving size is clipped at epsilon. Since too much perturbation can be easily found, we limit the maximum perturbation size by epsilon. And then we train the generated samples using the targeted model. This figure shows an image of the PGD method. First, we calculate the gradient of the loss function and then get the direction to increase the loss. We move a sample by alpha towards the direction. And we repeat several times to move the sample. The moving size is clipped by epsilon. This figure shows the classification boundary. The original classification boundary is a straight line. With adversarial examples, each sample may move up to epsilon. Finally, the classification boundary becomes smooth along the part of the samples. Next, I will show the proposed methods. First, I will show the overview of the proposed method. Our proposed method aims to expand the classification area of the minority, but important classes as much as possible. We thus consider expanding the decision boundary toward the majority class in order to avoid such misclassification. The right figure shows an example of the expansion. Our proposed method realizes this kind of manipulation by introducing weighted adversarial training to imbalanced learning. Here, we formulate the proposed method. Alpha prime and epsilon prime have nearly the same meanings as alpha and epsilon in the PGD method. Yet, alpha prime and epsilon prime consider the weights of the corresponding classes. Alpha prime y obtains the perturbation size at an iteration corresponding to each class. Similarly, epsilon prime y obtains the maximum perturbation size corresponding to each class. Since we regard that the minority class is more important than the majority class, we set variable as epsilon1 is smaller than epsilon2, and alpha1 is smaller than alpha2. The distribution of the perturbation is illustrated as the blue and green shaded areas in this figure. Based on the PGD-based adversarial example generation and training, the adversarial examples are generated as x1 and x2. As a result, the decision boundary can be described as the orange curve in the figure. Since the classification area for the minority class is expanded, the classification performance of the minority class is expected to be improved by the proposed method. In our proposed method, we take two approaches, untargeted and targeted. The untargeted method, called UTWPZD, aims to move a sample so as to maximize the loss. On the other hand, targeted methods, which is called as TWPZD, aims to move samples toward a specified class. In other words, it moves samples so as to minimize the loss with respect to a specified class. In particular, for multi-class classification, we expect that targeted model outperforms the untargeted model because we cannot control the moving direction with the untargeted model, which may invade another small class. In contrast, the targeted model moves the sample toward a specified class. So, for the multi-class classification, we expect that the target model outperforms the untargeted model. In addition to the weighted adversarial training, we introduce the balancing method when constructing a mini-batch. To balance the learning dataset during the training epoch, we draw the samples from the training dataset so that the number of samples in each class is even in the mini-batch. This figure shows the example. When binary classification, we pick up n samples from both classes and construct a mini-batch using them. In the mini-batch, the number of samples in each class is balanced. This is just a sampling method, but this should not affect the classification boundary. By combining this method and weighted PZT method, the classification boundary effectively expanded as we expect. And the next slide shows experiments and its results. In the experiment, we use multiple datasets included in CIC IDS 2017, which is designed to evaluate network-based IDS. CIC IDS 2017 has benign and attacked network traffic samples, and each record consists of the statistics of network traffics and its label that shows benign or attack types. Specifically, CIC IDS 2017 contains 7 datasets for machine learning purpose. In order to deal with the imbalanced classification, we use the 5 datasets in the CIC IDS 2017. We use a multi-layer perceptual model to train and classify the datasets. The structure and hyperparameters are shown here. In the evaluation, we focus on not missing any attacked samples. In other words, our top priority is to catch attacked samples as much as possible while keeping the total accuracy high enough. We introduce the evaluation matrix from the viewpoint of this priority. Therefore, we refer to the record to evaluate whether we have detected a minority class of attacked samples. This slide shows the results of our experiments. In binary classification results, untargeted and targeted models obtain the first and second highest record scores in all the models for each dataset. In particular, untargeted model outperforms other models in terms of record. It should be noted that a high accuracy score in imbalanced classification means that a classifier correctly classifies most of the majority class samples, not the minority class samples. Our goal in the presentation is to catch all malicious samples while keeping an accuracy score. In this sense, the proposed method works as we expected. The results are similar in multi-class classification, and the details is shown in the next slide. Now, I will show the details of the multi-class classification. The results of the DOS and PETATA is almost the same in both untargeted and targeted models. So here, we refer to the web attack results. The number of correctly classified samples in the web attack brute force and web attack XSS classes are unstable. The normal model could not consider the class distribution, and therefore classification boundary is not well constructed. The untargeted model adds perturbation towards the direction where the loss is most increased. In other words, the model cannot control the direction of the perturbation directly. Consequently, the perturbed sample might invade another smaller class, whereas we expect to invade a larger class. In contrast, the targeted model controls the direction of the perturbation directly, decreasing the loss as much as possible. As a result, the perturbed samples will not invade another class any more than necessary. Therefore, the targeted model successfully classifies them, considering class weight. In conclusion, the untargeted and targeted models successfully classify the real-world imbalanced datasets. When the dataset is binary class set, the untargeted model would be more effective due to the label leaking effect. Otherwise, the targeted model would effectively work considering the class weight. In order to analyze the class distribution obtained by the classifier, we visualize the test samples and the classes with TSNE methods. The TSNE method is commonly used to reduce the dimension of the dataset. Using the scatter plot obtained with the TSNE method, we visually analyze the data distribution calculated by the classifier. This figure shows the TSNE plots of the results using the infiltration dataset. The sample circled in red is misclassified as the majority class, whereas the untargeted classifier successfully classifies. From the results above, our proposed method, untargeted and targeted PZD, successfully work for the binary classification. In particular, the untargeted model expands the more classification area. To visualize the classification results of the multi-class classification, we select the web attack dataset. Originally, the dataset is difficult to classify. Edison and the untargeted model could not classify green samples in the classification results. In contrast, the targeted classifier successfully classifies several green samples, as shown in the red circle in the figure. So, the targeted PZD model successfully works for the web attack datasets. I will conclude this presentation. First, we designed weighted adversarial training to expand classification areas of minority classes. Here, we take two approaches, untargeted and targeted models. Then, we apply weighted adversarial training to IDS datasets. We show that our proposed methods successfully classify more minority class samples. Finally, we visualize classification results for further analysis. Here, we analyze the classification results with the TSNE method. For the future work, we will find out the method to optimize the perturbation size for each class. And that's all for this presentation, and thank you for watching this video.